First lecture on Chapter 5. Today we are going to talk about electrons in atoms. So we've all heard about electromagnetic radiation, and to some of you that may sound a little bit scary just because it has the term radiation in it. But you experience electromagnetic radiation all the time. You experience it when you listen to a radio, when you use a microwave, if you see, colors in a rainbow, if you have an x-ray taken, right? We have different types of electromagnetic radiation. It's not just this scary, this term radiation, right? That has a negative connotation. But electromagnetic radiation is light. And all types of electromagnetic radiation, including light, consist of particles that move as waves of energy, which should sound weird, right? The particles move as waves of energy, which is cool. So we're going to get into that today. So first, a little bit about waves in general. Waves of electromagnetic radiation are similar to the waves you might see at the beach, right? There's high parts to the wave and there's low parts to the wave. The highest part of the wave is called a crest. The lowest part is called a trough. And the distance between two crests is called the wavelength. And we're going to talk a lot about wavelength. And we use the Greek letter lambda, like that, to show wavelength. And it's always a distance between two crests, like I said. So two tops of the waves will be the wavelength. We also have two other terms. We have frequency, which we use like a V, essentially. It's like this. And that's the Greek letter nu. And that's the number of times the crest of a wave passes the point in 1 second. We measure this in hertz, which is the same as cycles per second or seconds to the -1. We're actually not going to do any math with this wavelength and frequency and speed, even though I will show you an equation to see how they're related. But right now we're just going to talk about them just so that we can understand how the waves are moving. So frequency you can think about is how close the waves are together as well as how fast they are going. So it kind of combines those two. And then speed, all of the electromagnetic radiation travels at the speed of light. And the speed of light, we use the letter C, and it's 3.00 times 10 to the 8th meters per second. It's really, really fast. So all light in a vacuum, anyways, is going to move at the speed of light, which is 3 times 10 to the 8th meters per second. But the things that can be different can be the frequency, which is directly related to the wavelength. If we have a really long wavelength, like this, right? If we have a really long wavelength, then something is likely to have kind of a low frequency. We won't see very many crests pass a particular point in a given amount of time. But if you have something with a really high frequency, or a short wavelength, like this, then we would see a shorter wavelength, which will mean a higher frequency. So we have this wave equation here, which is C equals lambda times nu. And this is just showing you here that wavelength and frequency are inversely related. Okay, so as the longer your wavelength is, then the smaller your frequency will be, or the lower your frequency will be. If we have a really short wavelength, then we'll have a really high frequency. So that's what this is here. In higher levels of chemistry, you will use this wave equation to calculate information about electromagnetic radiation. Maybe how long the wavelength is, or at what frequency is it. But we are just going to talk about it in kind of general terms. And so this wave equation is useful to us because C is a constant. It's always going to equal the speed of light. So if we have a really high, long wavelength, then we have to have a low frequency to get it to equal this number. Or if we have a really short wavelength, then we need to have a really high frequency to get it to equal this number. So they are inversely proportional, which means that as one goes up, the other one goes down. So as wavelength increases, the frequency decreases. They are opposites. Okay. When we have a shorter wavelength, like I said, that will correspond to a higher frequency, and a longer wavelength will correspond to a lower frequency. And we'll look at this electromagnetic spectrum here in a second. It's arrangement of the different types of radiation from the longest to the shortest wavelength. And what you need to know is that, if it's going from longest to shortest wavelength, that means it's going from lowest to highest frequency. Okay, and so our frequencies are what we associate with our energy. So if we have a really high frequency, then we're going to have a really high energy. Okay, and this will actually make more sense because you're familiar with a lot of these things when we get to the examples. So just a little bit more. So like if we have this red light has a really long wavelength, right? So we can measure it from either trough to trough, or we can measure it crest to crest. That's going to be the same. But this is going to have a long wavelength, which means it is going to have a low frequency, which means it is going to have a low energy. Okay, blue light has a shorter wavelength. So if we have a shorter wavelength, then we are going to have a higher frequency, which means this is going to be higher in energy. Okay, so we can tell all of this information from the wavelength, right? If it has long wavelength, then it's going to be low frequency, low energy. If it has a short wavelength, it's going to be high frequency, high energy. So if we look at this electromagnetic spectrum, on the left-hand side here, this is going to be things with a very long wavelength, which means that they are going to have low frequency and low energy. If we look at the other side, this side is where we have short wavelength, okay, which means it is going to have high frequency and high energy. And so this will make sense because you're actually familiar with a lot of this. Like we have power lines, right? Power lines and, radio waves. So like radio waves can reach up to a mile long, right? They can have a wavelength of a mile, which is crazy. And the reason for, this really long wavelength is so that you get reception pretty much anywhere. Like even if you're traveling through, the middle of the desert in Arizona, sometimes you can pick up this AM radio, but it's because of this really long wavelength that it can travel, around mountains and, into valleys and things like that. Okay, so it has very long wavelength and it has very low frequency and low energy, right? You wouldn't think of like, oh no, I'm going to get radiation from my radio. That would be strange. We also have, right, if we start to get, shorter and shorter wavelength moving this way, televisions, cell phones, microwaves. You may have heard things like, don't keep your cell phone next to your head, right? You're going to get radiation. Or, don't stand too close to the microwave. My parents used to tell me that one. Don't stand too close to the microwave because, you're going to get all that radiation. Well, you will get radiation because all of this is radiation. You'll get radiation just, standing in your living room, right? Because you have light. But it's not bad for you. That's the important thing here. We'll get into like this point here. I'm going to just draw a line. So we have all these different types of radiation, but the key thing here is the wavelength. Anything that has a long wavelength, so if it's a longer wavelength than this, like on this side, okay, all of the stuff on the left here has such a long wavelength that you actually can't get, quote unquote, radiation from these sources because the wavelengths are so long, they can't cause damage to your cells. Okay, so you can't get any kind of, hazard, there's nothing hazardous about your cell phone or your microwave because the wavelength is so long that it can't damage your cells. Whereas things to the right of this line that I've drawn have a short wavelength, and those are things that can do damage, like ultraviolet light, right? And where we see ultraviolet light, that's like from the sun. Right? You put on sunscreen to protect yourself from the UV rays because we know that UV rays can give you skin cancer. So that's why I'm telling you here. So this line is really important that I've drawn here. Stuff on the right, yep, you should be scared of that. Put on your sunscreen, right? But stuff on the left, it's okay. You can stand next to your microwave and look and see if your food is cooked or not. That's totally fine. Okay, back to some other things that are here on the left, like heat lamps. Heat lamps, or either, or infrared goggles, or if you play video games, sometimes they have like infrared sensing goggles on the video games that you can see the heat coming off of someone, right? That is a type of radiation as well. But again, it has a, long enough wavelength that it's not going to hurt you at all. Visible light is going to be here. It takes up a fairly small area of the electromagnetic spectrum, but we're going to spend a lot of time talking about it. If you haven't learned the colors of the rainbow, now is the time to do so. You need to remember Roy BIV. And I learned this in elementary school, but I know that some people didn't. So Roy G. Biv tells you the colors of the rainbow, and they are in order of decreasing wavelength. Red has the longest wavelength, and violet has the shortest wavelength, okay? And sorry, this stands for red, orange, yellow, green, blue, indigo, violet. If you hadn't seen it before, you might wonder about the eye, but it's red, orange, yellow, green, blue, indigo, violet. And you need to know this because we're going to use it for the flame test lab. Red has the longest wavelength, and it's going to therefore have the lowest frequency and will be the lowest in energy. Violet has the shortest wavelength, which means it will have the highest frequency and be highest in energy. And so we can use these colors to tell us information about how much energy is being released. And you can think about this in terms of fire, right? If you see like red and yellow flames, those are typically cooler flames. I mean, it's still on fire, but they're typically cooler flames than if you see like a blue flame. So that would be something that you can relate it to, right? Fire. Red tends to be a lower energy flame, whereas blue tends to be a higher energy flame. So those fall, like I said, right here in the visible spectrum. Typically things that have a longer wavelength than light, like I said, are kind of more lower energy, and then things that have a higher or a shorter wavelength than colored light will have a higher frequency. And that's where we tend to get into things like ultraviolet rays, and then you have medical x-rays, right? If you'll think about the last time you went to the dentist's office and you had to do x-rays, they always put that lead vest on you, and then, the dental hygienist leaves to protect herself from the x-rays. But the reason that they put that lead vest on you is to protect, all of your organs from any harmful effects of the x-rays. Because like I said, things on this side have the power to mutate your cells and cause damage and could even give you cancer. Like Marie Curie, if you've heard of her, she did a lot of work with x-rays, and she actually ended up dying from her research because of exposure to radiation. Okay, so always, make sure you have a lead vest on if you're going to go get a dental x-ray. And then gamma rays down here are actually one of the things that they use in radiation if you have cancer. They'll use this as a cancer treatment because it can go in and target cancer cells and kill them. So like I said, all of the stuff on this side can cause damage to your cells. All of the stuff on this side, the wavelengths are too long, you're generally considered safe from those. Don't forget, Roy G. Biv, that's how we're going to remember the order of the visible light. Okay, go ahead and find your Chapter 5 lecture worksheet and complete problems number 1 through 5. Oh, 1 through 4, my apologies. Okay, so when we have, if you have light and you send it through a prism, just like regular old light, and you send it through a prism, you're going to get a rainbow that comes through, which is really neat. So this is white light, and white light is going to be a collection of all of the colors of visible light. And you can shoot it through a prism, and it will split into different colors based on the wavelength. And this is what we see also when a rainbow is being produced. The light is hitting a raindrop, and it will produce a spectrum of this rainbow, which is really, really pretty. But it's because this light source over here contains all of the colors of visible light. So when it goes through the prism, it splits into all of the colors. Okay? But when we heat elements, they also produce light, but they don't produce white light like this. If we heat an element, then it will produce colors. So like neon signs, right? If we have a neon sign, you get this like red color. If you have a sodium street light, then you're getting like a yellow color. And so we're not getting a white light when we heat these elements, right? These atoms, we are getting colors. And what happens is the colors excite the electrons in these gases, and then it's able to produce this colored light, which is really, really cool. So that's what we're going to talk about today. That is what the flame test lab is based on. So the light is emitted from a heated element and passed through a prism. We don't get a continuous spectrum. We don't get a rainbow. Okay, and this is because it's not, it's not white light. It doesn't contain all of the colors of visible light. It only contains specific colors. And so like if it's, if it's showing red, it actually will have more colors than just red or than just yellow. But, red might be the dominant color or yellow might be the dominant color, but it doesn't produce a rainbow. It will produce really specific colors that are separated by dark areas. And we can actually use this to identify elements. We call this an atomic spectrum. Okay, so it's going to get bands of light. It'll have like a band, and then it'll be blank, and it'll have a band, and it'll have a band, and maybe some are close together. But then it's separated by dark areas. So it's not this continuous spectrum. It's not all of this where we see color the whole time. It's going to be color and then black and color and black. And like I said, we can use that to identify elements. The reason that it's got this, colored light separated by black light is because only certain wavelengths of light are produced by these heated elements. And we'll talk about why this is as we go through this lecture. So like if we had strontium, strontium's really pretty. It produces a really red light. And if we shoot this red light through a prism, it splits into a couple colors. Okay, again, it's not showing a continuous rainbow. It's only showing blue. And it's mostly showing, right, it's got a little orange and it's got some red. And again, this is not a continuous spectrum. This is an atomic spectrum. And we can actually use this to identify, oh, hey, this is strontium. Because if you look, strontium is completely different than barium. Barium produces this cool green light. And when you shoot the green light through a prism, it will split again into, kind of blue, green, orange, and red. But as you'll see, it looks completely different from strontium. So we can use these atomic spectra to identify which elements that we have. So here's hydrogen. Hydrogen doesn't have very many colors because if you'll recall, hydrogen is atomic number 1, which means that hydrogen has 1 proton, and to make sure that it's neutral, it also has 1 electron. So 1 electron is the one being excited because I told you these colors are produced when electrons are being excited. So if we only have 1 electron, we're not going to see a lot of colors because that 1 electron can only be excited to certain energy levels, which we'll look at in a minute. Mercury has more electrons, so we're seeing more lines. And neon has a fair number of electrons, so we're seeing lines as well. But as you'll notice, all of these are different, right? Mercury and hydrogen look completely different from neon, and so we can use this to identify what elements we have. So the reason that we're getting these really specific colors is because of the way the electrons are organized in the atom. We left off talking about Rutherford's model last time, where we said that there were protons and neutrons in the nucleus, and they were surrounded by electrons, okay? So protons and neutrons in the nucleus, they're surrounded by electrons kind of flying around the outside, and he called this the planetary model of the atom. And the reason that he called it the planetary model is that he said that electrons are orbiting the nucleus just like planets orbit the sun. And this was actually a really, really good model. It had the protons and the neutrons in the middle, electrons on the outside, which is still true today. But the way that he explained it, it couldn't explain any of these chemical properties of the elements. And so we needed a better model. Okay, and our better model ended up being Bohr's model. Niels Bohr was actually Rutherford's student. He took the work that Rutherford did and he included it. And what was really revolutionary is that he included information about how the energy of the atom changes when it absorbs or emits light. So he took all of this information about the colored band separated by black, and related it to the model of the atom. Like, why are we seeing these specific colors in these specific places? What is it telling us about the model of the atom? And he proposed that rather than the electrons just kind of zooming around the outside like this, he proposed that electrons are only found in specific circular paths. So like these electrons can only be on this path, and these electrons on the outside can only be on this path, right? And he called these paths orbits. And so he said, certain electrons can be in certain paths or orbits around the nucleus, and then when the electron gets excited, it can change which orbit it's on. Okay, so these these paths here, these orbits, we are also going to talk about as energy levels. And we'll get more into that last time, but these energy levels correspond to a specific amount of energy in an electron, or energy that electrons in an atom can have. As they are closer to the nucleus, they tend to be lower in energy, and as they get farther and farther out, they tend to be higher in energy. Okay. So in an atom, each electron has a specific energy level that it's been assigned to. And the way that we denote this is by whole numbers. So like this, anything on here, this will typically be energy level 1. The next one out will be energy level 2, and so on and so forth. So these are called principal quantum numbers, if you see them in your book. We'll mostly just call them energy levels in this class, but if you see the term principal quantum number, that's what it's referring to. So if you see this n, that's n equals 1, n equals 2, again, that would be like 1, 2, etc. And so they go all the way up to 7. Again, 1 will be the lowest in energy because it's closest to the nucleus, and as we go farther and farther out, they become higher and higher energy, and they will get higher and higher numbers. Okay. Electrons can only have certain energy values, and we call this that the energy of an electron is quantized. So if you see that term, that's what it means. It can only have a specific energy value, and this is because it can exist in energy level 1, or in energy level 2, or in energy level 3, right? But it can't exist at energy level like 1.5. You can think about this as like books on a shelf, or maybe rungs on a ladder, right? You can stand on the first rung, or you can stand on the second rung, but you can't stand in between them. So electrons can exist in this first energy level, or the second energy level, or the third energy level, but it can't exist at the 1.5 energy level. And again, as we get higher and higher numbers for our energy levels, our energy is going to increase. Okay, so higher energy electrons are located farther out from the nucleus. So here's what happens when we see this light being released, right? We're still trying to explain how these elements are producing these specific colors, where we have the color and the black, right? And how are they being produced? Well, what happens is we have an electron here, and so this electron is currently sitting in the first energy level, right? And again, electrons have to be on a specific orbital. They can't be between orbitals. So this electron is in the first energy level, but it could have been, it could be in the second or the third or whatever it is. And then electrons will always occupied in the lowest, electrons will always be found in the lowest unoccupied energy level. And we'll look more at this next time. Right now, though, we only have one electron, which means it will be in the first energy level because it's open. It will always sit as close to the nucleus as it can. So if we have electrons that are close to the nucleus, those are lower in energy, and the farther we get from the nucleus, then we are higher in energy. So the energy of the electron is depending on the distance from the nucleus. So when the electron is absorbing heat, so if we think back let's think about neon signs. If you turn the neon sign off, right, then there's no color coming through. But as soon as you turn the neon sign on, you're inputting energy. And then that neon, right, can absorb the energy from either, the electricity, or you could also use a heat source like we saw earlier when we were heating, right, with the flames, the strontium and the barium. So it just needs to absorb some energy in some way. Electricity or heat will do. And when the electrons absorb the energy, they become excited. And what that means is they change from a lower energy level and they jump up to a higher energy level. They absorb the energy, and this electron gets promoted to a higher energy level. So maybe it goes from the n equals 1 to the n equals 2. It jumps up in energy level. And when it jumps up in energy level, becomes excited, it has all this electricity, but eventually it will return to what's called the ground state. And when the electron returns to the ground state, when it returns back to that orbital that it came from, it will release all of that energy that it was holding on to, and it will release the energy as colored light. So if it releases low energy light, then that will be something like red. Remember Roy G. Biv, right? So if it releases low energy light, we might see red light. If it releases higher energy light, right? So if this electron here absorbs a lot of energy and then it gets promoted to a really high energy level, when it releases that light, right, it's releasing more energy, which means it will release a higher frequency of light. So we're getting something like green. So the color of light is telling us how much energy is being released or absorbed during this whole process, right? So if we have something like red, it's a really low energy, green or, violet would be a really high energy. So down here, the more energy that's being absorbed or released, the higher frequency of light that we're seeing. So again, we have an electron. It's getting hit with some energy, and that electron gets promoted to a higher energy level. When that electron releases that energy, right, and returns to the ground state, then it's releasing that energy as colored light. So here's what it looks like. We have an electron. It absorbs the energy, right? It absorbs all this energy, and it gets promoted to a higher energy level. And this is called the excited state. And then eventually, that electron will return back to the ground state down here. And when that electron returns to the ground state, it releases all of that energy as colored light. The farther the electron falls, right, the bigger that jump, the more energy that's being released. And like I say over here, the color red we associate with the lowest amount of energy, and the color violet will have the highest amount of energy. So this is how the colors are being produced in those spectra that we were looking at earlier with the lines, right? Those are telling you how much energy is being released by these different electron jumps. And we can use these different electron jumps to tell us which elements we are looking at, which is really, really cool. So this is what we're going to use when we talk about the flame test lab, which will be coming up shortly. So now I want you to go ahead and complete problems number 5 through 6